ADAS stands for Advanced Driver Assistance Systems, which refers to a range of technologies designed to enhance vehicle safety and driving experience. These systems help drivers with tasks such as controlling the vehicle, monitoring surroundings, and improving overall driving comfort. ADAS uses various sensors like cameras, radar, LiDAR, and ultrasonic sensors to provide real-time data and assist with tasks. Common examples of ADAS features include Adaptive Cruise Control or ACC adjusts the vehicle's speed based on the distance to the car in front, maintaining a safe following distance. Lane Departure Warning or LDW alerts the driver if the vehicle unintentionally drifts out of its lane without signaling. Lane Keeping Assist or LKA actively steers the car back into its lane if it starts to drift. Automatic Emergency Braking or AEB detects an impending collision and automatically applies the brakes to prevent or reduce the severity of a crash. Blind Spot Detection or BSD warns the driver if another vehicle is in their blind spot. Traffic Sign Recognition or TSR identifies and displays traffic signs such as speed limits on the vehicle's display. And finally, Park Assist helps the driver park the vehicle by controlling the steering and sometimes braking, while the driver manages the gear and throttle. These technologies are becoming more common in modern vehicles, and as they advance, many of them are moving toward full automation, also known as Level 5 autonomy in the future. ADAS plays a crucial role in the development of self-driving cars. ADAS or Advanced Driver Assistance Systems works by using a combination of sensors, cameras, radar, and software to monitor the vehicle's surroundings, interpret the data, and provide real-time feedback or control. Here's a breakdown of how it works. 1. Sensors and cameras. ADAS relies on multiple types of sensors and cameras to collect data about the vehicle's environment. These sensors can include cameras, which are used for detecting lane markings, road signs, and vehicles ahead. They provide visual data to the system. Radar sensors are used for detecting objects at longer distances and in low visibility conditions, like fog or rain. Radar can track the speed and position of vehicles or objects ahead of the car. Ultrasonic sensors are used for close-range detection and are often employed in parking assist features. They help detect obstacles close to the car. And LiDAR, or light detection and ranging, uses laser beams to map the surroundings in 3 dimensions and provides highly detailed data about the environment. 2. Data fusion. The data collected by these sensors and cameras is sent to a central processing unit, usually a computer or ECU, which stands for Electronic Control Unit, within the vehicle. The system uses data fusion to combine information from multiple sources to create a comprehensive understanding of the vehicle's surroundings. 3. Processing and interpretation. Once the data is collected, the system processes it using advanced algorithms, often based on machine learning and AI, to interpret the environment. For example, object detection involves identifying and classifying objects like other vehicles, pedestrians, road signs, and lane markings. Trajectory prediction anticipates the movements of objects and vehicles around the car, like predicting when another vehicle will merge into the lane. Mapping and localization use high-definition maps and GPS to position the vehicle accurately on the road. The system then compares the real-time data to pre-programmed rules or behaviors to decide what action should be taken. For example, if a vehicle is too close to another car, the system may alert the driver or activate automatic braking. Driver alerts and interventions. Based on the analysis of the data, ADAS can either provide alerts or take autonomous actions. Alerts. If the system detects a potential risk, such as an imminent collision, lane departure, or an object in the blind spot, it will notify the driver through visual, audible, or haptic signals. Interventions. In some cases, the system may intervene to prevent accidents or assist the driver. For example, automatic emergency braking or AEB. If the system detects an imminent crash, it can automatically apply the brakes to avoid or mitigate the collision. Lane Keeping Assist or LKA. If the vehicle drifts out of its lane without signaling, the system will apply slight steering inputs to bring the vehicle back into its lane. Adaptive Cruise Control, or ACC, maintains a safe following distance by adjusting the car's speed based on the traffic around it. Levels of autonomy. ADAS is often associated with levels of driving automation defined by the SAE, or Society of Automotive Engineers. These levels range from 0, which is no automation, to 5, which is full automation. Most ADAS features today belong to Level 2 automation, partial automation, where the system assists with driving but requires the driver to remain engaged and ready to take control. Continuous learning and improvement. Advanced systems use machine learning to improve over time. As the car's sensors collect more data from various environments, they help the system become better at identifying different driving conditions, road types, and obstacles. This data can also be shared with manufacturers to improve future software updates. Example: how Adaptive Cruise Control, or ACC, works. Sensors. The car's radar and cameras continuously monitor the road ahead to detect the distance and speed of vehicles in front. Data fusion and processing. The system uses algorithms to determine if the car ahead is slowing down, maintaining speed, or speeding up. Control. If the vehicle in front slows down, ACC will reduce the speed of your car to maintain a safe distance. If the road clears, it will accelerate back to your preset speed. Driver alerts. The system may alert you if it cannot maintain a safe distance or if the road is too crowded. Summary. In essence, ADAS combines hardware, such as sensors and cameras, and software, like algorithms and machine learning, to monitor and interpret the driving environment, helping with tasks like steering, braking, accelerating, and alerting the driver to potential hazards. Over time, these systems evolve toward greater automation and may eventually allow for full self-driving cars or Level 5 autonomy.